Tonight, we're going to explore one of the most fundamental aspects of reality: gravity. You experience it every single moment of your life. It keeps your feet on the ground. It keeps the atmosphere around Earth. It keeps Earth orbiting the Sun. It governs the motion of galaxies billions of light years away. And here's the twist that's going to change how you see the universe. Gravity isn't actually a force at all. It's something far stranger and more beautiful than that. Before we dive in, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin this journey into understanding what gravity really is. Consider what you think you know about gravity. You drop an object and it falls down. Simple, right? You've been told since childhood that Earth's gravity pulls things toward the ground. That gravity is a force pulling you downward. That the Sun's gravity pulls Earth into orbit around it. Most people believe exactly that. Schools teach exactly that. And while it's not exactly wrong, it's incomplete. It's like saying the Earth is flat because it looks flat when you're standing on it. It works for everyday purposes, but it misses the deeper truth. Isaac Newton figured out the mathematics of gravity in 1687 when he published his book Mathematical Principles of Natural Philosophy, usually just called the Principia, one of the most important scientific works ever written. Before Newton, ideas about why things fell or why planets moved were mostly philosophical guesses. Newton changed everything. He showed that the same force that makes an apple fall from a tree also keeps the moon orbiting Earth and Earth orbiting the sun. Revolutionary because people thought the heavens and Earth operated under completely different rules. Newton unified them with one set of mathematical laws. Newton's law of universal gravitation states that every object in the universe attracts every other object with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me break that down. Earth, and you pull on each other hard because Earth is massive. You and a pencil across the room also pull on each other, but so weakly you'd never notice it. Exactly how weak are we talking? If you tried to build a gravitational wave-style detector sensitive enough to register a single person walking past the lab, the two arms of the interferometer would need to be roughly the distance from our star to Saturn. Approximately 10 billion kilometers, or 6 billion miles long. Anything shorter, and the signal is completely swamped by quantum and thermal noise. That's why you can feel the tiniest magnet or a static shock from a doorknob, yet two people standing a meter apart attract each other gravitationally by less than the weight of a single bacterium. Gravity is 39 orders of magnitude weaker than the electromagnetic force on everyday scales. One of the deepest unsolved mysteries in physics, and that's before we even get to the inverse square law. Double the distance, and the pull doesn't halve, it drops to a quarter. Triple the distance, and it falls to 1/9. That's what makes gravity dominate only when the masses get truly enormous. Newton's equations worked beautifully. They could predict the motion of planets with incredible accuracy. They explained tides, the ocean rising and falling because of the moon's gravity pulling on the water. They explained why planets farther from our star move slower in their orbits. They allowed scientists to discover new planets by observing tiny irregularities in the orbits of known planets. That's how Neptune was discovered in 1846. Astronomers noticed that Uranus wasn't moving exactly as Newton's equations predicted. They calculated where an unknown planet would need to be to cause those deviations. They pointed their telescopes at that spot, and there was Neptune. right where the math said it should be. For over 200 years, Newton's laws were considered the final word on gravity. But there were small problems. The most famous was Mercury's orbit. Mercury orbits in an ellipse that slowly rotates over time, called precession. Newton's equations predicted how much Mercury should precess based on other planets' gravity. But the observations didn't match. Mercury was precessing roughly 43 arcseconds per century more than predicted. That's approximately 1/80th of a degree per century. Incredibly small, but real and measurable. Scientists searched for explanations. Maybe an undiscovered planet called Vulcan was pulling on Mercury. It didn't exist. Maybe Newton's laws needed adjustment. Nothing worked. The mystery remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's insight was radical. Gravity isn't a force at all. Rather, it's a curvature of space-time itself. That probably sounds like meaningless word salad. Curvature of space-time. What does that even mean? Let me explain it step by step, building up from concepts you already understand. First, consider space and time separately, the way we normally think about them. Space is the three-dimensional arena where things exist and move. You can move forward and backward, left and right, up and down. Those are your three dimensions of space. Time is different. It flows in one direction from past to future. You experience events in a sequence. You can't move backward in time or jump forward arbitrarily. Space and time seem fundamentally different. Space is where things happen. Time is when they happen. But Einstein showed that space and time are not separate. They're woven together into a single four-dimensional fabric called space-time. Not just a mathematical trick, a description of physical reality. You can't have space without time, or time without space. They're aspects of the same thing. When you move through space, you also move through time. When time passes, you're also moving through space-time, even if you're sitting still in space. Every event in the universe happens at a specific location in space-time. Not just space and time separately, but space-time as a unified four-dimensional structure. Here's where it gets interesting. Space-time is not rigid. It's flexible. It can bend and curve. And what causes it to curve? Mass and energy. Any object with mass or energy curves the space-time around it. The more massive the object, the more it curves space-time. Earth curves space-time around it. Our star curves space-time much more because it's much more massive. Even you curve space-time a tiny amount. Everything with mass or energy curves space-time to some degree. Think of space-time like a stretched rubber sheet. If you place a bowling ball on the sheet, it creates a dip or depression. The heavier the ball, the deeper the dip. If you roll a marble near the bowling ball, the marble doesn't travel in a straight line. It curves toward the bowling ball, following the slope of the depression. From the marble's perspective, it's just following the straightest path available. But because the sheet is curved, that path curves toward the bowling ball. Similarly, Earth curves space-time around it. When you drop a ball, the ball isn't being pulled by a force. It's following the straightest possible path through curved space-time. That path happens to curve toward Earth's center. The analogy has limitations. The rubber sheet is a two-dimensional surface, being bent in a third dimension. But space-time is four-dimensional, and it's not bending into some higher dimension. It's intrinsically curved, meaning the curvature is a property of space-time itself, not a bending into something else. Also, in the rubber sheet analogy, we're using gravity itself to make the ball sink into the sheet. That's circular reasoning when we're trying to explain gravity. So the analogy is useful for visualization, but don't take it too literally. What does it mean for space-time to be curved? The rules of geometry are different. In flat space, the shortest distance between 2 points is a straight line. But in curved space, straight lines don't exist in the usual sense. Instead, there are geodesics, the paths that represent the shortest distance between 2 points in that curved space. On Earth's surface, which is curved, the shortest path between two cities isn't a straight line through the air if you had to stay on the surface. It's a curve following what's called a Great Circle route. Flights from New York to Tokyo fly over Alaska. It looks like a strange curved path on a flat map, but on a globe, it's actually the shortest route. In curved space-time, objects follow geodesics. A planet orbiting our star isn't being pulled by a force. It's following a geodesic through the curved space-time created by the stellar mass. From the planet's perspective, it's moving in a straight line. But because space-time is curved, that straight line from our perspective looks like an orbit. The planet is constantly falling toward our star, but also moving sideways fast enough that it keeps missing it. A perpetual state of freefall. This explains why astronauts in orbit around Earth experience weightlessness. They're not beyond Earth's gravity. The gravitational field at the altitude of the International Space Station, which orbits roughly 400 kilometers, or approximately 250 miles above Earth, is still around 90% as strong as it is on the ground. The astronauts feel weightless, not because there's no gravity, but because they're in freefall. They're following a geodesic through curved spacetime. Earth curves spacetime, and the space station follows that curvature, constantly falling toward Earth, but moving sideways fast enough to keep missing it. The astronauts inside are falling at the same rate as the space station, so relative to the station, they float. You experience the same thing when you jump. For the brief moment you're in the air, you're in free fall. You're weightless. You don't feel your weight pressing down on your feet. Of course, the moment is so brief, you don't really notice it. But if you could somehow extend that moment, remove the ground so you kept falling, you'd feel exactly what astronauts feel in orbit. True weightlessness. Picture yourself in an elevator and someone cuts the cable. Terrible scenario, but stick with me. As the elevator falls, you'd float inside it. You wouldn't feel your weight. You'd be in free fall along with the elevator. Alternatively, imagine you're out in deep space far from any planet or star. You and the elevator are drifting. You'd also float inside because there's nothing to push against. Einstein's insight. These two situations are equivalent. Free fall in a gravitational field and floating in deep space with no gravity are the same experience. You can't tell the difference from inside the elevator. The equivalence principle. One of the foundational ideas of general relativity. Similarly, standing in an elevator on Earth, you feel the floor pushing up on your feet. That's what weight is, the floor resisting your tendency to follow a geodesic through curved spacetime. In a rocket in deep space, far from any planets or stars, if the rocket is accelerating at 9.8 meters per second squared, roughly 32 feet per second squared, the same acceleration you experience from Earth's gravity, you'd feel the floor of the rocket pushing up on your feet in exactly the same way. From inside the rocket, there's no experiment you could do to tell whether you're standing on Earth or accelerating in deep space. These two situations are equivalent. The equivalence principle leads to some strange predictions. One, is gravitational time dilation. Time passes at different rates depending on where you are in a gravitational field. The stronger the gravitational field,